Hello, ladies, gentlemen, and non-binary, and welcome to our webinar partnered with DigiKey Electronics, the exclusive sponsor of our Würth electronic webinars. My name is Amelia Thompson. I'll be your host for today's webinar, and our presentation today is toroidal flat wire PFC inductors versus the traditional PFC inductors, of course, partnered with DigiKey Electronics and presented by our very own Würth Electronics, Stephen Chung, product manager professional for our custom magnetics division at Würth Elektronik. Now, if you have any questions during today's webinar, please feel free to ask them in the questions box, and we'll get around to them at the end. However, if your questions don't get answered, or maybe you think of them a little bit later, make sure you reply to our follow-up email from webinarteam@we-online.com. You will be getting that because you registered for today's event. So you'll automatically receive the presentation slides and the video on demand when they become available. Again, simply look for that link in your email. You can also scroll down to the handouts section and download today's slides and follow along with our presenter. Our final webinar is coming up in just a couple of weeks, Tuesday, November 28th. Join us for definition of component heating of powerinductors in switching regulators. Register online at www.we-online.com/webinars or click the link in that follow-up email. Now let's begin today's Würth Electronic webinar with Stephen Chung, toroidal flat wire PFC inductors versus traditional PFC inductors, partnered with DigiKey Electronics.
Okay, so hello everyone. My name is Stephen Chung, one of the product manager of Würth Electronics, responsible for power isolated products. So welcome again for the webinar today. So today I would like to share with you about what is PFC and our product portfolio for PFC inductors. So let's begin. So we are going to discuss about the following topics: why we need to use PFC, and we have two different types of PFC. One is the passive one, and the other one is active. And I'm going to show you our standard PFC series in our portfolio, and also what are the features of our standard PFC series. So what does PFC means? PFC means power factor correction. And basically PFC choke or PFC inductor shapes the input current to be in phase and amplitude proportional to the mains voltage, as you can see in this waveform. And why do we need to use PFC is to avoid reactive power, which have to be provided by energy suppliers on top of the active power. In other words, the reactive power is representing the energy that bounced back from the user to the utility company, resulting in unwanted losses and power line distortions. So here, I show a typical schematic of PFC circuit. So you can see it is a three-phase input. However, of course, you can see this three-phase input, and there are 6 switches. So for three-phase input, 3 PFC inductors will be used. And the output voltage after the PFC circuit will be about 800 volt DC. But of course, here I only show an example for three-phase input, but in reality, single-phase AC input can use PFC circuit also. And for single-phase AC input, the output voltage will be 400 volt DC. Sorry, I missed something on the last slide. So as you can see, the output voltage is 800 volt DC. So it is very important that we select components when we design a three-phase PFC circuit that can operate in a long term that in under the output voltage of 800 volt DC. So here we can visualize the following signals by this waveform. The first one is an input current with no PFC. And the second one is an input current with passive PFC. You can see the waveform is a bit distorted. And the input current with an active PFC is shown on the number 3 waveform. And number 4 is the input voltage. So you can see with the active PFC, the waveform of current and voltage are in phase. So we can minimize the reactive power. So here, I'm showing we have this kind of traditional bobbin PFC series. We call it the WE PFC series. So this series has been in the market for a very long time. And it is using traditional bobbin type structure, namely RM series, which has small footprint and good EMC behavior due to the shielded type core and the grounded core. And it has low AC winding losses due to we are using the least wire. And also we have EFD series, which provide a flat design, which is critical for applications with height limitation. And also for the EFD bobbin, we are using low AC, we are using least wire to minimize the AC winding losses. So for the standard PFC choke series, for this kind of bobbin structure, we have a series that is designed for universal AC input, which is from 85 volt AC to 265 volt AC. And we offer a wide range of inductance and saturation current, which can fit with different switching frequencies. And the power rating is up to 250 watts. And we have even more choices for European AC input, which is from 195 volt AC to 265 volt AC. So once again, we have a lot of inductance for customer to choose, and we provide different saturation current level for the traditional PFC choke series. So next one, this is the new series that we developed or we launched it this year. We call it the WE-TOR, stands for Toroidal PFC. As you can see, this series is not using the traditional bobbin type structure. Instead, we are using flat wire on a toroidal core. We use flat wire windings instead of traditional round wire or least wire because we like to minimize the DCL and allow for better cooling. We are using different core material rather than ferrite to provide a high saturation current with soft saturation features. And we designed to make the operating temperature range from -40 degrees Celsius to positive 155 degrees Celsius. And we also designed a robust mounting system by ourselves. As you can see, there's a plastic base plate and a cover, which help us to help this series to comply or to pass the ACQ200 vibration test, which is in nowadays the market always require ACQ200 reliability tests for the high power products. So here is a overview of our standard of the new Toroidal PFC series. So we have a total of 17 parts, offering a variety of different sizes and inductances. This makes the series a fit for a wide range of power levels and application. So you can see we have 3 different sizes, different inductances, and different saturation current level. The specification of rated current are with and without airflow. We do different tests to show the rated current under different conditions. And we have do some comparison with our competition and found that our parts are smaller for the same inductance and the rated current level. So here is a closer look of the photo of the actual part. As I mentioned earlier, this PFC series use PFC flat wire, to allow us to get a lower DCL and also has better cooling characteristics. this allows the series to achieve higher rated current and lower losses. And on the data sheets, as you can see on this right-hand side, I capture one example, which we show the temperature rise in different conditions with a fan cooling of 1 meter per second, 2 meter per second, and 4 meter per second. So you can see with the fan cooling, the rated current can change drastically. And we always recommend, why we are showing this is because we like to show to our customer the actual performance of the inductor under the fan cooling condition. And we also believe that for such high power applications, fan cooling are usually available. So here is showing the specification of a part in the Toroidal PFC series. As you can see, we are putting both the insulation test voltage and the operating voltage. Like I mentioned earlier, the operating voltage of 1000 volt DC is to ensure that it can work under the three-phase AC input circuit and to accommodate the trend of higher working voltages in the market nowadays. So we perform detailed measurements in our development. In our datasheet, we are showing a curve of inductance versus the DC bias current, and we are defining the saturation current as 30% inductance drop. However, it doesn't mean that our part cannot operate beyond the saturation current. If the inductance level requires match with the peak current in the circuit, the part can still operate well. So we are defining the saturation current of the inductance drop in 30% drop, but the part can still operate actually beyond this 30% inductance drop. Like for this part, it can operate well in a 150 amp and 80 microhenry inductance. And also, like I mentioned earlier, we did measurements of rated current under different cooling conditions. And we always recommend our customer to select the part with the suitable rated current according to the cooling condition they plan to use. And this can help them to avoid selecting a part which is overrated and resulting in a larger size or higher cost of the product. So here is a closer look again, which you can see we put a strong base and a cover plate. And what I like to highlight here is that this unique plastic base and cover provide enough protection to pass the AEC-Q 200 vibration testing. And besides of protecting the parts from vibration, it helps to add insulation between the start and finish of the winding, resulting in an improved rated voltage. And also, the plastic-based design help for easy mounting to the PCB. Customers do not need to spend time and worrying about how to reliably mount these large parts onto their boards. And here we have did some measurements comparing a flat wire inductor with an equivalent round wire inductor. As you can see, the flat wire design has lower temperature rise, which is shown in the orange curve here, and the blue curve is by the round wire. And you can see the temperature rise is higher for the round wire design, and the temperature rise is lower relatively when we are using the flat wire design. Like, for example, under 14 amps current, the temperature rise difference is about 12 degrees. So we are using here the same copper size of round wire and the flat wire. And they are wound on the same toroidal core to make sure that we are doing a apple-to-apple comparison. And the reason of the lower temperature rise is because the flat wire design has a better cooling effect. And this measurement is actually measured under the condition of without fan cooling. And we believe that the difference of the rated current or the temperature rise would be even bigger if the measurement was done under fan cooling condition. So here, as shown in the table, you can see one of the critical parameters is the intra-winding capacitors. And we found that this is very critical for such high power application. And as you can see here, flat wire windings design show a much lower intra-winding capacitance for the same wire size and on the same winding, on the same toroidal core. So how we can use these PFC inductors, the new toroidal PFC inductors, and we can find that in very high power applications such as the solar inverters, EV chargers, telecom PSU, and also industrial or medical AC to DC power supply. These are the common applications that will use these toroidal PFC inductors. So that's the end of my sharing. If you have any questions, please feel free to send in the chat box. I will try my best to answer your questions.
Thank you very much, Stephen. We do have a few questions rolling on in, and as he mentioned, feel free to ask them in the questions box, and we will hopefully get them answered today. But again, if we don't, simply reply back to our follow-up email or email us at webinarteam@we-online.com. So our first question here, why are there parts with the same size and DCR but different saturation currents?
That's a good question. Sorry, can you repeat that again?
Yes, just a second. My screen has decided to minimize itself. It says, why are there different parts with the same size and DCR, but different saturation current?
Oh, okay, I see. So let me think how to explain this. In this series, as you can see, we have 17 parts, and in fact, we are using two different types of core material for in this series and among these 17 parts, and they are both iron powder core material, but we are using two different types of iron powder material with different saturation features. One of them is with higher saturation current. However, it has a higher cost. And according to our research, we found that some applications do not require such high saturation current level. So we decided to use two different core materials, but the same core size and the same windings to offer two different choices for our customer to select the part based on the saturation current level they prefer to use or they need to use.
Excellent. Thank you very much. A few more questions rolling on in here. Your second one, why is this new series, the We TOR PFC series, why do you select flat wire windings but not Litz wire windings?
We found that based on our research or the information we collect from the market, typically the PFC circuit, which as I mentioned in the first few slides for the active PFC circuit, and it is using the topology of CCM, or we call continuous conduction mode. And typically it operates in the frequency range of 65 to 100 kilohertz. And we found that in this frequency range and high rated current application, lowering the DCR and increase the cooling area of the windings is more critical than lowering the AC losses. And for least wire, it is good for lowering the AC losses. So in this frequency range of 65 to 100 kilohertz, we believe that the performance or the losses is lower if we use the flat wire winding. And the last thing is we found that flat wire is more suitable for the winding process on a toroidal core, which we plan to use in this series by iron powder toroid. And flat wire is, I can say, is more manufacturing friendly when we like to use flat wire windings on toroidal core. So that is why we select flat wire windings instead of the least wire windings.
Excellent, thank you. Our next question here, how do you select a suitable PFC inductor for an application? This might be a little broad, but hopefully you can give us a general overview.
I can try my best. So I think that the first thing is to calculate or to estimate the root mean square current of your application and also the peak current of your application. That's the two most critical parameters that you have to know. And the second thing is to know the inductance you need at the peak current. And if the user or the customer, they look into our website, we are showing the rated current and the saturation current. But I would suggest don't just read or check the rated current and the saturation current in the front page or in the table of our website. Instead, you can check the charts in our datasheet. Like I mentioned in my presentation, the rated current can be varies or increase a lot with the appropriate fan cooling or even other types of cooling system. And you can select a part with suitable rated current from the curves, which we try our best to do different measurement to provide more information about the rated current from the curves. And our PFC inductor can operate beyond the saturation current, like I mentioned in the presentation. So do look at the charts in our data sheets to find a part with the inductance you need at the peak current level.
Thank you very much. We have a few questions coming in about the production of the component. Can you explain how the choke is produced? Do you use a split core, or how do you insert the flat wire windings?
That is how to say. I would say it touched with some of our design proprietary info, but I can say that yes, is the core is cut first, and then we do the windings first, make I can call it forming the windings, and then we insert the windings into the two core halves, and then we stick them together. That is all I can say.
Understandable. We're going to roll on into our final questions. There are more questions, but we will be reaching out individually to those people. Final question here. Why do flat wire inductors have a much smaller inner winding cap than flat wire inductors?
It's because of the area that is overlapping. As you the least wire is made by I would say, many strands of very tiny wires, and the touching area of those areas is very large. And instead, as you can see from the photo, the flat wire windings, for each turn of the winding, they are separated with a certain distance. And this helps to lower the intra-winding capacitance, actually. So, and you can see also in my presentation, the photo that I've shown in of the, I call it the prototype that we use the least wire for winding. Each turn of the least wire winding, they are very close to each other, and that is why the intra winding capacitance is very high comparing with the flat wire windings.
Thank you so much, Stephen, for presenting today's webinar. I really appreciate it.
No problem.
And thank you, everybody, for joining us. Again, if you have any questions, simply reply to our follow-up email, the questions that we have not gotten to today. We will be reaching out to you individually. For our next webinar and all other information, please feel free to follow Würth Electronics on LinkedIn. You can also follow myself, Amelia Thompson, Amelia, for those who are confused on the spelling. I grew up with that, so I completely understand. And don't forget to listen to the new episodes of the Würth Electronic What's Up podcast. Each week we are bringing application notes, blogs, press releases, and our webinars to an audio and a video format. And that is the What's Up podcast. It can be found on all podcast streaming networks like Google Podcasts, iTunes, Spotify, and so much more. And join us for our final webinar as we present definition of component heating of power inductors in switching regulators, coming up in a couple of weeks on Tuesday, November 28th. Register online at www.we-online.com/webinars. I'm Amelia Thompson, and I hope to see you soon.